Good morning, everybody. Welcome back from spring break. Only a few weeks to go, and then we're done. Hallelujah. So, um, today we're going to start off on our next chapter, which I think is chapter 20, which is going to be on electrochemistry. And in here, we're going to see how we're going to apply concepts of thermodynamics to essentially understand how we can get chemical reactions to generate electricity, or how we can use electricity to generate chemical reactions. And so we'll be kind of exploring that this chapter. First, though, we're going to kind of have to do a little bit of a review. And so we're going to first kind of start off by remembering that electron transfer reactions which are going to be the ones that can generate electricity, are going to be what we commonly call as redox, if you remember from last semester, where we have a reduction and an oxidation happening. And remember that oxidation was the process of losing electrons, and reduction was the process of gaining them. I guess I need big parentheses here. So we have kind of both of these processes happening at once. And we're going to see that if we can kind of throw a wire in there, make a circuit out of this, we'll be able to kind of keep track of the electricity that's flowing as things are going from our oxidized species to our reduced species. So yes, good morning, good morning. Actually, I guess I forgot our announcement of the day. I sent out an email like about an hour ago or so. We're going to push exam 3 1 week, so it's not going to be next week. It'll be 2 weeks from now. So we're just going to push it back a little bit, just so I can throw in the non-metal chapter on you guys as well, because why not? We like to do that sort of thing. So we'll talk closer to the date of that, but now it's 2 weeks from now, so the 19th instead of the 12th. So we'll have a little bit extra time there. Cool. So there's our announcement. Anyways, we should kind of do a little bit of a review to kind of start getting us back in the idea of redox stuff. Remember we had these things called oxidation numbers, where we could kind of keep track of our electrons as they go from one component to another in a reaction. We kind of referred to this as kind of electron accounting before. And we remember we had a couple of rules that we were able to apply when talking about oxidation numbers. We remember that elements in standard state by themselves have an oxidation number of 0. Remember, so just like, yeah, exactly. So standard state would be 0 for those, so that would be something like hydrogen gas or aluminum, whatever, these things would just be 0. If we look at the next one, we talked about simple ions. That would be monoatomic ions. We saw that the oxidation number was equal to the charge. So we saw, for example, with these particular ions, they're simple ions. This one has an oxidation number of +1. That one has an oxidation number of -1. So simple ions just had their charge equal to their oxidation number. We remember that the sum of oxidation numbers in a compound or in a polyatomic ion would be equal to the charge of the polyatomic ion. And then lastly, we saw kind of if all else fails, we start with electronegativity order. And then we basically follow preferred charges based on electronegativity. And remember, we do this in a particular order, so sometimes you'll have oxygen as -1 instead, or something else. Just depends on what it's with. But we have to start with fluorine, then hydrogen, then oxygen, then the rest in essentially electronegativity order. We would just give them their preferred charges as their oxidation numbers. And so kind of rule 4 is kind of our, well, we have to make sure that rule 3 is followed there to make sure that we have a neutral compound at the end of the day here. So if we do a couple, let's see. Here's one of our favorite redox reactions, perhaps. It is a nice single replacement reaction. If we were to look at the oxidation numbers of these, we can start off with our kind of easy ones, the ones by themselves we don't have to worry about. Those are always going to be 0. In this case, they're solids, but I've omitted that because I'm lazy. Next thing, we can look for some common ions in here. We see that silver nitrate, for example, is an ionic compound. So we know it's made of these 2 ions. We note that the silver ion is a simple ion. So we know that the silver here must be +1. And so now we have to then kind of remember that when we have the rest of the compound, we're going to have to deal with everything else. So we have to, kind of tally up our elements here and set that equal to 0. Hopefully this process is somewhat familiar. We saw that silver was +1 because it was a simple ion. And if we look at our rules, we're going to deal with oxygen before we deal with nitrogen. We do this, we solve, we get nitrogen as +5. And so we end up with the following oxidation numbers. And then if you just do the rest, you'll see the copper is going to be +2 at the end of the day. The nitrogen is still +5, the oxygen is still -2. And yeah, Kevin is already ahead of us here, which is awesome. So what we can see here is overall what's happening in this reaction. If we look at kind of overall, if we have our reactant side and product side, we had these elements, silver, nitrogen, oxygen, and copper. We saw that we started with silver in the +1 oxidation state. It went down to 0. Nitrogen started +5, ended +5. Oxygen started -2, ended -2. We already have the span, that's lovely. And then we saw that copper went from 0 to +2. So we remember our mnemonic, perhaps, where we have oxidation is losing, and then reduction is gaining. And we can see here that this process of the copper going from 0 to +2, that's losing electrons, right? So we can see here that this copper is losing electrons, becoming more positive. So that's going to be the process of oxidation. And the silver is going to have the opposite, where it will be undergoing the process of reduction. And if we remember way back when, we have names for these things. We end up calling these agents, right? We saw that the element that is reduced is part of the oxidizing agent. And then vice versa, right? The one that is oxidized is part of the reducing agent. And so we're going to say here that our silver nitrate will be our oxidizing agent. And remember, agents are always going to be part of our reactants. And so we're going to see that copper will be our reducing agent. And just remember, agents are always reactants. So whatever your elements are part of in the reactants that are undergoing the oxidation or reduction, those are going to be part of your agents, potentially. So we always look at the product or the reactant side for this. All right, so hopefully this is kind of just a review. If you want more practice, just like go to my YouTube, find last semester's things. You'll find the oxidation numbers and like kind of practice on that. You can just have a look at that video perhaps if you like. But hopefully this is not too new. So hopefully that'll be good. So just kind of a little refresher there for this. We're going to see that we'll be spending a lot of time looking at oxidation reductions in this chapter because that's what we're interested in. So, any questions on those ones? Hopefully nothing terribly new again. It may just be a little rusty. When did we do this? Like chapter 4 or so last semester? So it'll be somewhere towards the earlier side of the semester, maybe a couple weeks in. Alrighty, cool. If we looked at, by the way, the net ionic equation for this process that we just looked at, we see that we're going to end up with an overall reaction of this. This is our kind of net ionic equation, right? Of what's happening here. I'm omitting state symbols because I'm naughty, but you know, solid aqueous is what you'd have there. With this, what we often look at in electrochemistry is we look at these as half reactions instead. We see that this is actually two half reactions. That make up this net ionic equation. We see we have I guess I'll put some state symbols here. We have kind of two processes happening at once. We have the silver being reduced, and then we have the copper becoming oxidized, right? And notice if we were to add these two equations together, we would end up canceling out the electrons, right? Because that's the whole kind of point of this. And so we're going to see that we can kind of then combine these reactions together. If we add them, we'll end up with our net ionic equation again. I'll just copy everything right now, and then we'll cancel out our electrons. So as always, we just get rid of stuff that is identical on both sides, and we end up with our net ionic equation that we had before. So we can totally do this sort of thing. So we're going to see that when we're going to look at these sorts of redox reactions, we're going to be kind of selecting half reactions to put together. And so very often we're just going to be looking at half reactions and throwing them together. And we're going to see that when we're balancing redox reactions, things get a little bit more tricky than they would if we were to just balance them normally. We're going to see that, unfortunately, redox reactions don't just kind of happen in this nice kind of, oh, my electrons have zipped away from copper, now they're on silver, and end of the story. There's a lot of kind of help happening from the water. We're going to see that these reactions often take place in either aqueous or acidic solution. And so if we were to really look at what's happening, we have a way to do that. So this is kind of easy mode, right? But then we have reality to come over here. So what we're going to see is that we're going to have a process to balance half reactions out before we add them together. And so we'll be able to kind of look at that. So we can go ahead and start with this example if we want. We can start with balancing it in an acidic solution. Let's learn how to do that. Let's balance these half reactions first in acidic solution. So, you know, it is always nice to say, okay, yeah, we have this reduction happening here, end of story. But you know, when we're dealing with kind of more complicated ones that are not just one atom gaining an electron, we're going to see things become a bit more complicated. So let's look at a kind of a more complex example. So I have quite a few from our book that we can use. Let's start with, how about we do this one? So let's take a look at this reaction. So we have sulfur plus nitric acid turning into sulfurous acid and what? Nitric N2O. Okay. So when things are more complicated, let's balance them. We're going to have to balance them a little bit more delicately than we would be able to otherwise. So if we kind of look at what's happening here, if we can kind of separate these into the half reactions, well, we're going to probably want to isolate the things that are going to be essentially, we're looking at what's being oxidized, what's being reduced, right? So we're going to want to go ahead and do our oxidation numbers for all of these things. One of them we can do right away. Hopefully we see that that sulfur should be 0. If we do all this oxidation number stuff, the nitrate we already did last time, so that one's done. Here we have, I guess we can do this for an example. So we have sulfurous acid. So that means we have 2 hydrogens plus a sulfur plus 3 oxygens equals to 0. We know the hydrogen is +1, the oxygen will be -2 according to our hierarchy. And so sulfur ends up being +4 as a result. So that's +4. And of course our oxygen would be -2. And then, yeah, for the last one, we get nitrogen is +1, oxygen is -2. So if we look at this overall, we've got our reactants and products. We have sulfur going from 0 to +4, hydrogen +1, +1. Nitrogen was, what, +5 to +1? Yeah, and then oxygen stayed the same. So we can see here that our oxidation, the losing electrons, is the sulfur, right? Sulfur is being oxidized. And we are going to see that we are going to end up with the reduction here as a result. And so if we want to kind of see what's happening, if we're looking at the half reactions here, we can kind of see, okay, let's take our sulfur 1 and our nitrogen 1 separately. So we know we're going from sulfur to sulfurous acid. And so if we want to take a look at kind of what's happening here, we have a process to balance this sort of equation. So we can see here we just have sulfur turning into sulfurous acid. That's a very exciting half reaction, said no one ever. But we're going to see that we have a way to do this. So we want to first balance the non-oxygen or hydrogen elements. So in this case, that would be sulfur. So we're going to want to balance sulfur out first. We have 1 on each side, so we're done with this step. So that's kind of the first step for doing this. Then we want to balance out oxygens by adding water as necessary. So if we want to balance out our oxygens, we have 3 oxygens on the right side. We have 1 or 0 on the left side. Hopefully that part is obvious. So if we want to balance that out, we can add 3 waters. So now our oxygen is balanced. Next, we want to balance out the hydrogen. And this time we're going to add H plus to both sides, or rather as necessary. And Kevin, of course, has already gone ahead and done all of this, which is just fine. So if we look, we have 6 hydrogens on the left, 2 hydrogen on the right. So we're going to want to add 4 to the right side to balance this out. So now we have our 4H plus here. And then we're absolutely right. Our last step is to balance the charge. By adding electrons. So if we look here on our left side of the reaction, we'll take a look at that Star-Lord in just a little bit. So we're going to see that when we have the other half of the reaction. Yes, and that's also true, Kevin. Yeah, you're always going to have oxidation as having electrons as a product. That's definitely true. So if we see here, overall we have no charge on the left. We have 4 positives on the right. So we're going to want to add 4 electrons to the right side to balance this half reaction out. So, oops, I guess well, whatever, that's good enough. And so this would be kind of our balanced half reaction for the process that's happening here, the oxidation of the sulfur. we're going to see that when we add the half reactions together, what's going to happen with all this sort of stuff. And we're going to see that because this reaction is taking place in acidic solution, we're not going to necessarily need to cancel out all of the H pluses. We're going to see that we can balance stuff in basic solution instead, and in that case, we're definitely going to neutralize all our H plus. But let's go ahead and take a look at that second half of the reaction. We had, I think, nitric acid turning into N2O, if I remember correctly. Yes, we did. So let's balance this one. So step one, we're going to balance non-hydrogen or oxygen. So that means nitrogen in this case. So let's just go ahead and throw a 2 here. Step 2 is we're going to balance the oxygens. And if we look here, we have 6 oxygens on the left, 1 on the right. So we're going to add 5 waters to the right side. Then we balance hydrogens. If we look, we have 2 on the left, 10 on the right. So we're going to add 8 hydrogens. I'm sorry, I'll try to do these in color so you can see what we're adding each time. And then the last part is we want to balance the charge. And so if we want to balance the charge, you see we have 8 positives on the left, so we're going to need 8 electrons as well on the left to cancel that out. Okay, so we have done all the steps for this half reaction now. So that one's done. And so if we take a look at our last half reaction, take a look at this one. I'm just going to make the electrons a little bit obvious here. Oops. So these were our 2 kind of half reactions, right? If we were to add these up right now, we would see that our electrons wouldn't cancel out, right? What we need to do is, if we're going to put these now together, is we're going to have to multiply this whole thing by 2 so that we can end up with 8 electrons on both sides. So we want to always, just like with stoichiometry, we want to make sure that all of our coefficients kind of match up. So let's just go ahead and do that. If we see that we have now 2 nitric acid plus 8 H plus 8 electrons, turns into our dinitrogen monoxide. Now we have 2 sulfurs plus 6 waters, turns into 2 sulfurous acids, plus 8 H plus 8 electrons. Right, so we want to make sure that these, when we're balancing these together, that the electrons will cancel out. That's the important thing. We never want to see just kind of rogue electrons flying around. So we always want to make sure that you We'll kind of multiply as necessary to kind of balance the electrons in the two halves. That's what we've done here. And now we can add these guys up. If we do that, and you get something crazy long, but let's just do it. 2 nitric acids plus 8H plus 8 electrons plus 2 sulfurs plus 6 waters. Okay, well, we'll just kind of write it this way. Doing all this fun stuff, we see that we are going to cancel out our hydrogens, our electrons. We're going to cancel out 5 of those waters. And so we're going to see overall what we need for this reaction to be balanced. Oops, I forgot a water. Turns into N2O plus 2 sulfurous acids. Oof. All that work just to throw in the extra water, right? That was the only thing really that we ended up doing, right? So if we kind of look at our initial reaction that we started with, we just didn't have that water, right? Everything else was essentially just the same, slightly doubled, I guess, to balance stuff out. But we did end up having that one extra water here. So we are going to see that, unfortunately, these do need to be balanced as half reactions and then put back together before you can just kind of balance a redox reaction like this. So they're a little bit trickier to balance than regular old reactions. And so yeah, in this case the H plus is canceled out, so we don't have to worry about them. Sometimes they won't, just depends. Let's do this again. Let's do another one. How about we do, yeah, let's do this one. Are there any questions on that one, by the way? As I start writing down the next one, bromate plus hydrazine turns into bromide plus, okay. So let's balance this in acidic solution. Hopefully this one we can see the half reactions pretty easily. Doesn't matter which one we do first, but I'll do the bromate one because I see that one first. That's just the way I like to do it. What type of thing is this going to be, by the way? We have, for oxidation purposes, we have plus, what is this going to be, plus 5? So this is, by the way, since we're on the practice, this is going to be a reduction half reaction, right? Yeah. It's important later because we're going to see that when we're talking about electrochemical cells and batteries and that sort of thing, it's important that we know which one is the reduction, which one's the oxidation. So with that, let's go ahead and balance this. So first we want to balance the bromines. They're already balanced, so let's go ahead and start now with oxygens. So it looks like we have 3 oxygens on the left, so let's add 3 waters to the right. so that was kind of our step 2. So we balanced oxygens. Step 3 is hydrogens. We have 6 on the right. We need 6 on the, look at, yes, indeed, yes. We will see that what happened at the cathode, yes. But that's definitely later on here. If we balance hydrogens, we need to have 6 of them now to balance out. And then our last one is the electrons. So we see that we have a total charge of positive 5 on the left, negative 1 on the right. So we're going to need 6 electrons, right, to make everything balance out. That's awful. Hopefully that is okay. So that one is done. Let's look at our other one. We had the hydrogen here. We're going to go ahead and do that one. So if we look at that one, we had N2H4 turning into N2. Hopefully, without even needing to worry about this, we know this is the oxidation half reaction. We know that because the other one was the reduction, so this has to be the oxidation. But if we wanted, we could see that these are going to be minus 2 to 0, so that's going to be increasing as we go. So let's start out balancing nitrogen, we're done. Balancing oxygen, we're done. Let's balance some hydrogens now. And then if we want to balance the electrons, we can do that. Alrighty, so that one is now balanced. Alright, and then so now we want to combine them. Let's take our first reaction here. Our second reaction. If we look at the electrons here, if we look at the electrons, we see that we have 6 and 4. We want those to be the same, so we're going to have to balance them out. We want to do kind of the least common multiple. If we have 6 and 4, both of those will go into 12, right? So if we want to make these into 12, we have to multiply this one by 2 and this one by 3. And hopefully, I'm just going to just do that all at once if that's okay with everybody. 2 bromates plus 12 hydrogens plus 12 electrons plus 3 hydrazines turns into 2 bromides plus 6 waters plus 3 nitrogens plus 12 hydrogens plus 12 electrons. And now we see here, okay, the electrons should cancel. That's the big thing here. Indeed, our H pluses will cancel out. Lucky us. And I think that's all that's going to cancel here. So overall, we have 2 bromates plus 3 hydrogens turns into 2 bromides plus 6 waters plus 3 nitrogens. And we're done. Hooray! any questions on that one? All right. Let's take a look at one in basic solution and see that it's really not that different, I suppose. Um, there are a couple of ways to go about it. I think the easiest one is to just first balance it in acidic and then cancel out the H pluses. Let's take a look at an example. Let's see. How about we do this one? We have nitrite. Oops. Plus aluminum turns into what, aluminum oxide, or oh, interesting. Plus what, ammonium? Yeah. Okay, let's try to balance this in basic solution. We're going to see if we balance in basic solution, all we have to do, I mean, you could balance it by adding OH minus to both sides instead of H plus, but then that messes with your waters and things get complicated. So it's a little bit easier to just balance it as if it were acidic and then just cancel out the H pluses. And so we're going to see that first, just balance as acidic. And then we'll go from there. So let's just balance this one as if it were in acidic solution. All right, so half reaction, we have nitrite turning into ammonium. Yep, exactly. You just throw in OH minus at the end to cancel out the H pluses, and that's the only difference. Alrighty, so if we do this, we see that the oxidation numbers that are here, again, this is just for kind of practice here. We have -2, so this will be +3. We have +1, so this will be -3 as a result. So hopefully, I mean, this is going to tell us we need 6 electrons right here, but we're kind of cheating by doing the oxidation numbers, but that's okay. Looks like the nitrogens are balanced, so let's go ahead and do the oxygens next. Two waters is what we'll need here to balance the oxygen. So first balance nitrogen, 2 and then 3. Then we balance oxygen, then we balance hydrogen, and then we'll balance the electrons, right? Just like before. So second step now, we're going to balance hydrogens. We have 4 plus 4, 8 on the left. Or we're going to need 8 on the left, rather, because we have 8 on the right. Next, we're going to balance the electrons. If we see we have overall +7 on the left, +1 on the right, we're going to need 6 electrons. Indeed. And so if we are going to want to take into account our basic solution instead, we're now just going to add enough OH minus to both sides to cancel out all the H pluses. All right, and so if we do that, we're going to add 8 hydroxides to both sides. And as Kevin has noted, this becomes water. Becomes 8 waters, in fact. And if we notice, we have 2 waters on the right, 8 on the left. So overall, let's just subtract 2 waters. And now what we're left with is our nitrite ion plus 6 waters and our ammonium and 8 hydroxide ions. All right, so this is the easier way to balance it in basic solution instead. Otherwise, you'd have to worry because now you're throwing in oxygen and hydrogen to both sides. It just makes it more complicated if you were to try and balance it with hydroxides instead of H pluses. So this is the easier way to go. But as you can see, this is still a somewhat kind of time-consuming process, right? We haven't even touched our second half reaction, which was aluminum to that, whatever that is. Yeah, let me stop putting lines everywhere. Maybe I'll just put a big break. We've got whatever magical ion this is for the other half reaction. As we can imagine here, this should be a reduction because the last one was oxidation, if I remember correctly. No, the other one was reduction, so this is going to be our oxidation reaction. If we have that, that's minus, so we need plus 3 over here. And so this, of course, that will be our oxidation, just to have it. We have aluminum's already balanced. Let's go ahead and balance oxygens. So we get that. So first was aluminum, second was oxygen, third now hydrogen. So if we do that, we have 4 on the left, we need 4 on the right. And then the fourth one is electrons. So it looks like we have an overall plus 3 on the right, 0 on the left, so we need to add 3 electrons. And remember, again, we can kind of cheat. We already know that the aluminum is going to be losing 3 electrons through this process. We saw that with the oxidation numbers. So if you ever kind of get stuck again, you can kind of cheat. Just look at the oxidation numbers. You'll see how many electrons are involved in that process. All right, step 5 now is to do the hydroxides. So we're going to add 4 hydroxides to each side. I guess I should have done that to the left side, shouldn't I? Was it 4 hydroxides? Yeah. And then we have our 3 electrons. That'll make 4 waters. So we're gonna have 2 waters from the other side, canceling them out. So we'll have 2 now on the other side. If we balance this, ta-da! Oof, so much work. All right. And now we can take our previous reaction and let's add them up. If we see here, we have 3 electrons and 6 electrons. So we want to, here, I'll be a little bit clearer because I know there's tons of reactions happening here. There are tons of like equations. I'll copy this one down here. We want to add these together. we're going to need to multiply this one by 2 so that the 6 electrons will cancel out. If we do all this fun stuff, we get NO2 plus 6 waters plus 6 electrons plus 2 aluminums plus 8 hydroxides turns into ammonium plus 8 hydroxides plus 2 aluminum weird ions plus 4 waters plus 6 electrons. We see hydroxides cancel, electrons cancel. We're going to end up with 2 waters, and then we're done. Hooray. We get all of this fun stuff. Woo! Isn't that exciting? Lots of work for balancing an equation, right? Whew, how exciting. We only have 7 minutes. I can't really go anywhere further, can I? Can we just do one more then? Just for practice, I guess, since we have the time. Let's do another one. Alrighty. Last one then. So today is just on balancing redox reactions, I suppose. Alrighty. Hydrogen peroxide. Chlorine dioxide. This is going to be just, just oxygen. Alrighty. And let's do this one in basic solution. So basically we've done problem 26 on the homework here. Just all of these reactions. Because why not? It's fun. Alrighty, first things, chlorines. Sorry, we have to separate these first. So we know we're going to have the chlorines will go together, of course, right? So we're going to have this as one of our half reactions. This is going to be, we've got +1 going to 0. Oops, sorry, -1 going to 0, which is going to be an oxidation, right? No, this is a reduction. No, it is oxidation. Yeah, we're becoming more positive. Okay, so we're losing electrons there. And then we're going to have our, wait a second, why can't I think about this? Oxidation is losing electrons. We are losing electrons. Okay, yeah. All right, so with this one, we want to balance non-hydrogen and oxygen. Of course, we can't do that. Balance oxygen, we're done. Balance hydrogen, we can do. We want to now balance electrons. Hopefully I can just do that here, if that's okay with everybody. Cool. I'm cheating. Now let's do our hydroxides. Turns into oxygen plus 2 waters. I hope it's okay that I'm just blowing through this, if that's okay. If I'm going too fast, let me know and we'll slow it down a little bit. But hopefully this is not too bad. We've done this all day. So that's half reaction 1, half reaction 2. Hopefully this one is real easy to do. Aha! Exciting stuff, right? We don't have hydrogens, oxygen, chlorine already balanced, so there's no need for bases in here. So we just needed to balance the electrons out. Alrighty, so doing this, if we were to put these two reactions together, and our second reaction was we can see here we're going to need to add two of these to balance out the electrons. So in doing this, oops, oxygen plus 2 waters plus 2 electrons plus 2 of these chlorites. Electrons cancel, nothing else cancels. So overall, so here's an example where we indeed keep our hydroxides here this time. We did not need any to balance the other half reaction, so in basic solution we still end up with some hydroxides here. So, hooray, we did it. So there we have it. Balancing redox reactions, we did it. So, lots of fun stuff here. So, and it looks like we're pretty much out of time. So with that, we'll continue kind of tomorrow. We'll talk about putting these reactions together in an electrolytic cell or a galvanic cell. We'll make some electricity. We'll throw in some delta G stuff because I'm sure you're happy to talk about that again. So we'll go from there. All right. With that, I'll see you guys tomorrow. Enjoy your day.